Hello friends, today I am going to show you how to calculate the work function of aluminium 111 plane through density functional theory. The software that we will be using for calculation, for DFT calculation, is OpenMX. It's a free software. You can download it and install in your computer. For crystal modification, we will be using another free software, Vesta. It's also so first it will be used for the crystal modification. So the first step is to load the zip file of aluminium unit cell in the Vesta. So let's begin. So this is the unit cell, this is the zip file for the unit cell of aluminium, and here it's a unit cell for aluminium. Now the first step, what we will do is to increase the number of atoms in all the three directions. Let's say I increase it to 5 in all the three directions, and okay. So now we have sufficient number of atoms for cutting the 111 plane slab. Now we will go to edit and go to lattice plane, and we will create a new plane. Currently its color is red. We will choose blue color. Let's say we choose the blue color and 111 plane. Okay, so now as we can see, this is our 111 plane. Now let's rotate it in this direction to make it more clear. Yes. Now we will bring this plane in between somewhere over here. So let's say we move it by 5. So now this is our 111 plane. Now we will be needing one more 111 plane exactly parallel to this plane, and we have to keep in mind that the crystal symmetry is maintained. So we have to look for the atom that is exactly symmetrical to this atom or this atom. Any one of the atom we can choose. So now we can clearly see the symmetrical atom to this one is this atom, and this one is a fifth row. So 6, 7, 8. So on the 8th atom we have to cut another plane. So we will now create one more plane, same color, blue. It's a 111 plane. Okay, so now we have two 111 plane parallel to each other. Now we have to draw the planes that are perpendicular to these planes. So let's now rotate this this cell to this direction. Okay, now we will select this atom, and this atom, and go to lattice plane, and now we will make a new plane, and let's name it, give its color red. Okay, now we will calculate the best plane for the selected atom. Now we have selected these three atoms, and we will calculate the best selected. So it automatically gives you the plane that is perpendicular to these two planes, that is 111, and the new plane that is formed is 1, 0, -1. Okay, now we have to make one more plane to complete a unit cell that is parallel to this 1, 0, -1 plane. So what we do is we select this plane and again make a new plane, and let's say give here 2. Yes, 2. 2 is more, let's 1. So this is another 1 0 minus 1 plane that is parallel to a previously drawn plane. So now this completes our unit cell. So this portion over here is our complete unit cell that we will be selecting. It's a 1 1 1 plane in this direction over here, and 1 0 minus 1 plane in this direction. So now we will be deleting the extra atoms. Let's say we will select all the atoms that are not required. Delete. Delete. Now we have deleted most of the atoms which are not required. Now we have to reduce this reduce the size of the unit cell in this direction. Sorry. So now this is our unit cell. We have reduced the number of atoms in the unit cell. So now this is our new unit cell. Now we have to choose one atom as an origin. Now since we will be calculating the work function along 1 1 1 plane, so what we will do is we will select this direction as a direction, this direction as a B direction, and this direction as a C direction. So it's now we will be choosing this particular atom over here as an origin, and we will note down its coordinates. This is 2 1 2, 2 1 2, and we will be choosing this atom in a vertical direction as a plane. So it's 3 2 3. And this particular atom as in the B direction, it's 2.5 1 1.5. And we will be choosing this atom for calculating the C for our unit cell. It is 1.5. Yes, it is 1.5 to 1.5. 1.5 to 1.5. Now we will be calculating using these ABC values. We will be calculating the values for our new unit cell, that is A dash, B dash and C dash. So here A dash is C2 minus B2. That means this A value minus origin 3 minus 2. Similarly B dash X will be D, that means 2.5 minus 2, that is 0.5. So we will subtract each value from the origin and we will get the corresponding XYZ values for the A dash, B dash and C dash. These are the new coordinates of our unit cell. Now we will modify our unit cell. We will again open the same CIF file of aluminium. So this is the original CIF file in which we did the modification. Now we will modify its unit cell. We will go to edit data, unit cell, transform. So here we will modify the unit cell values. So new values are 111, 0.50 minus 0.5, and minus 0.51 minus 0.5. So now we have modified the values for unit cell. Yes, search atoms in the new unit cell and add them as a new site. We will select this second one and apply. Okay, so here this is our new unit cell after modification. Now for work function calculation, so now this is our new A direction, and yes, this is our A direction, this is our B direction, and this is our C direction, the same way we have selected in our when we were cutting the planes. Now we will calculate the work function of aluminium using this new unit cell. Now in this unit cell, as already discussed, this plane is 111 plane and this is along the A direction. Now we have to calculate the work function along this direction, along the A direction only. So we will now further modify this unit cell for work function calculation. First of all, we will create a supercell along A direction only. So we will go to edit data, unit cell, and remove symmetry, transform. Now we will enter 2 over here, so and leave other places, other values same. Okay, yes, and we will select second one. Okay, apply. Okay, so now this is our new supercell. Now in this supercell we have created supercell only along A direction, and we have not added the atoms in B or C direction. Now the other modification that we have to do for the work function calculation is to add vacuum at the bottom and at the top of this unit cell. So for this, what we will do, we will increase the length of the unit cell along A direction by approximately 70 angstrom, and we will shift these atoms towards up direction by 12 angstrom. So this will create a vacuum space at the bottom and vacuum space at the top of the unit cell. So now to do this, we will now export the data in the WASP format. We will remove the cube format, we will save it in a WASP format and then save. Now before saving, what we will do is remove the boundary atoms, because there are total number of atoms over here are 27. So for calculation, it is better we should reduce the number of atoms so that the calculation time can be reduced. So in this case, what we will do is we will change the boundary condition in Y direction. We will change from 1 to 0.99, and in Z direction change from 1 to 0.99. So this will reduce the number of atoms in both the directions, especially the boundary atoms. So now the number of atoms are reduced from 27 to 14. Now we can export the data, the coordinates. We can export the coordinates in the VASP format. So I think it's a previously saved file. So we will replace it in the VASP format. Save, replace. We will save the Cartesian coordinates, not the fractional coordinates. And then here we will only save output coordinates of all the displayed atoms. We will only be saving the atoms that are displayed over here in the supercell, not the atoms that we have actually removed by boundary conditions. So we will press OK, and then we will go to the VASP file. We will open the VASP file, and this is the VASP file. So in the VASP file we have 14 atoms only, and these three are the coordinates of our unit cell. This one is for the A, and this one is for the XYZ for the A, and these are for the B, and the third one is for the C. So now we will increase the length along the A direction, so we will make it 73 angstrom, and these are the Cartesian coordinates of the atoms. So what do we want to shift the atoms to the up direction along the x-axis. So what we will do is we will add the 12 angstrom to the each value in the x. So here we will replace 0 with 12. 13 plus 12 will be 25. 12 plus 6 will be 18. 12 plus 2 will be 14. This will be 21. This one will be 16. This one will be 23. 14. 21. 16. And this one will be 23. Here 12. This one will be 25, and the last one will be 18. Now we will save the file, and we will reopen this file in Vesta. Here it is. This is the file. So now, as we can see, the atoms are the length of the unit cell along the A direction is increased to 73 angstrom approximately, and each of the atoms are shifted by 12 angstrom from the bottom. So as you can see over here. So now again this Vesta automatically takes the boundary atoms. So again the number of atoms are 27. So we have to reduce these number of atoms by boundary condition. So we will again reduce them from 0.99 in y direction and 0.99 in z direction. So after reducing, number of atoms are again 14 atoms. Now as per the tutorial of as per the OpenMX tutorial of calculation of the OpenMX for work function, calculation of work function, we have to basically we have to replace the aluminium atoms at the boundary with the empty atoms. So the empty atoms are basically the so how to basically remove these atoms, aluminium atoms with the empty atoms. What we can do is over here, so these are the boundary atoms over here. This one, this one, this one, and this one. These two atoms we will be replacing, aluminium atom will be replacing the empty atoms. So in OpenMX, the empty atoms are denoted by E. So here we will first of all, what we will do is first of all we will export these coordinates in a fractional coordinate system. So we will go over here, export data, XTL. So now we will replace them in the we will now save them in a save the fractional coordinates. Save. Now we have saved the fractional coordinates. So these are the fractional coordinates. Now we have to remove the atoms at the boundary with the empty atoms. So this is the mandatory for calculating the work function. So this atom we will be removing, and this atom we will be removing, this atom and this atom. So this particular atom, now what are the fractional coordinates? 0.16, 0.00 and 0.00. So we will change them over here. So first atom, this is the 0.16, 0.00, 0.00. So this atom we will be replacing with empty atom. Symbol is E. Now this is the another atom we have to remove. So 0.16, 0.5 and 0.5. So 0.16, 0.5 and 0.5. So we will replace it with empty atom. Now over here 0.35 and 0.0, 0.0. So we will be replacing it with the empty atom. So this one is replaced with the empty atom. And the last atom we have to replace is this one. So it's 0.35, 0.5, 0.5. So 0.35, 0.5, 0.5. This atom will also be replaced with the empty atoms. Now we have to copy these coordinates to the input file for OpenMX. So now we will go to the input file for OpenMX in OpenMX folder. So this is the input file that I have already created. So here we are defining the number of atomic species that we will be using is 2. One is the aluminium atom and another is the empty atom. These are the pseudo atomic orbitals for aluminium. So in empty atom also we will be using the same pseudo atomic orbitals, and this is the file for pseudo potentials for empty atom, and this one is for the aluminium. And now here we have 14 atoms that we have to add here. So we will be adding our fractional coordinates of the atom over here. So these are our fractional coordinates. We will copy them. Copy. And now we will edit it according to the format of OpenMX. We have to add the serial number to each value. So and here we have to add this upspin and downspin electrons. So in this case, since the spin polarization is off, so both the number of electrons in upspin and downspin should be equal. So in empty atom we will take it as 0.0 because empty atom doesn't have any electrons. So copy them, copy. For aluminium, upspin electrons and downspin electrons are 1.5 each. So 1.5 we will take. So this is the format for OpenMX that we have to do. So now we have copied all the coordinates. I think one is left at the bottom. So now, right, now here we will enter the values of the unit cell. So unit cell values were in the VASP file. Now these are the unit cell values. Unit cell coordinates we will enter over here. These are not in the right format. Make them in the right format. Now we will be using GGA PV approximation, and spin polarization is off. Other values are default. Cutoff energy we will taking as 150, and we will eigenvalue solver is band, and SCF K grade is 1 cross 1, 4 cross 4. Now in this case, one important thing is the ESM switch has to be kept on 1 because it's vacuum, because we are using vacuum on both the sides over here. We are using the vacuum on both the sides of a slab. So in this case we will be using, in ESM configuration we will be using on one means vacuum our unit cell and then vacuum. Also you can read more about this effective screening medium on this tutorial of OpenMX. So here you can read more about it, and there is another section about effective screening medium in detail. You can read in section 47. Now after this we will save the unit cell, and now we will run the calculations. Close without saving. Now we will go to DFT, OpenMX, work. So we will again check our unit file. Is it, everything is on perfect. Now this is our terminal. Now we will just run the calculations. OpenMX al111.dat. Okay, there is some error in the coordinate system, and number of atoms. Check in the input files. Okay, I think there is some error. Let me check. Okay, fractional coordinate, I think it is, we have to enter these values inside this atomic coordinate. These two values we have to enter. So by mistake I entered them outside the function, so that's why it is giving an error. So now we will again run the calculations. So now they are running fine. Now I will skip the calculation part because it will take quite long time, and since I am also recording this video, so it may also freeze my laptop. So I will stop the recording here and again start the recording after some time. Now after a successful completion of the calculations, many output files will be formed in the work directory of OpenMX. And one of the important files for work function calculation that we will be looking is .v0.q. This file contains Consham potentials in the 3 dimension. Now we can plot this Consham potential. This is our unit cell that we have used for the calculations, and we can open this. We can open the Consham potential in Vesta. So now this is our Consham potential. Now we can see these Consham potentials are in the 3 dimension. Now for work function calculation along a direction, we have to convert these 3-dimensional Consham potentials to one-dimensional Consham potentials. So in order to convert them, we will be using the command provided in the OpenMX package. So this is the command. It will convert this 3-dimensional cube to the 1D plot. Now this file is formed after the conversion. We will copy the text and plot it. We will be using QTI plot for plotting the data. So now these are the one-dimensional Consham potentials along the A direction. The value is in Hartree. Now we will calculate the work function. Now the first equation, the work function is equal to the Consham potential at the infinite distance minus chemical potential. Now if we look at the graph, the Consham potential at the distance of 70 angstrom is approximately 0. So in this case our work function will be equal to the chemical potential. So now we have to look for the chemical potential. Chemical potential is present in the different file, that is al111.out. So we will open this file, and here we can search it in, this is the search option. We can search for the chemical potential. So it is over here, and the value is around 0.162. So we will copy this value and convert it to, this value is in Hartree, so we have to convert it into electron volt. So it is around 4.40 electron volt. Now So this value is around minus 4.408 electron volt, that is equal to 4.408 electron volt. Now, so the calculated work function, measured work function of the aluminium is around 4.2, and our value that we have calculated through DFT is 4.408 electron volt. We can further improve the accuracy of our result by relaxing our structure, by reducing the forces inside the structure. That's a different topic. Now, if you have any question regarding this topic, you can ask me in the comments, and if you want me to make some other videos on density functional theory, so please comment in the video. Thanks for watching.